let's talk about orientation in 3 dimensions. We've already talked about rotation in 2 dimensions, other things in 2 dimensions. Let's think about what orientation means in 3 dimensions. There are some different words that go along with this: orientation, angular displacement, that involve angular displacement. Kind of says you're starting in a starting position and doing some motion to end up someplace else. Orientation is trying to describe where an object, how an object is situated in 3 dimensions. And we had talked about the idea that if you had a vector, you could have rotation that would be in this direction or this direction in 3 dimensions. So we can rotate in different directions. And if we had an object, we could do that same kind of thing. And then we also have a rotation like this. And so if you had an object and you rotate it, it changes the object. If you just have a vector and you rotate, it's still just a vector. But if you have an actual object, we get 3 different kinds of rotations that are possible. And so in terms of each of those different directions, one approach is trying to describe all this in matrix form, but there is an approach called Euler angles. And the Euler angle approach is, again, there are multiple ways to describe this, and different industries that need to use these have described them in different ways. But we're going to think about what happens in terms of, we're going to describe the transition from an object space to the original upright space. But what we have is we're going to have 3 angles. One that describes one type of rotation, the other 2 describe 2 different types of rotation. And we'll use our author's approach to this. Our author describes these 3 angles in terms of heading, in terms of pitch, and in terms of roll. So let's think about our left-handed system that we've been using for some situations. Our left-handed system has plus x to the left and plus y up. So what does that mean about the third component? It's facing away from us. Right? So our left hand. So heading corresponds to, in this situation, a rotation about the vertical y-axis. Right? This is this rotation. What does pitch correspond to? Pitch corresponds to a rotation about, so think about an airplane, right? Heading is, which direction are you flying? What is pitch? Pitch is, are you flying level or not, right? It's like this. And then what would roll be? Roll would be this way. So let's think about the axes that we're talking about. Heading is rotation about which axis? That's the vertical axis. Which way is positive rotation or positive heading? Well, again, we have the left hand. So what do we think about? We need the left hand rule. Positive rotation. Thumb up, which way the fingers curl. That's positive. Right? So from this perspective, that's the positive rotation. If we're looking down from the top, that looks like clockwise rotation. All right. What about pitch? Pitch is rotation about the x-axis. Which of those is positive? Down is positive in that case, right? So looking at it from this direction, Again, that looks like clockwise. What about roll? And which is positive there? That way is positive. All right, so looking at it again from the end of the axis. All right, so what do we have from inside the object? We have our different. These are our different rotations, right? And so what the Euler angle does is it gives an angle for each one of these, and then we need to figure out what's happened. But what happens when you rotate something? When you rotate something in 3 dimensions, once you change the heading, and then say you do a pitch, so now your plane was going this direction as far as this standard, but now we've rotated it and it's pitched down. What happens when it rolls now? Does it roll about this axis? No, it rolls about the new one. So changes over here affect what's happening to the actual object, right? So the coordinate system has gone with it, and so we roll about the new thing. One problem with this situation with Euler angles is that if we, for instance, went a rotation, we went all the way around like negative 135 degrees, went around this way, did some things, we can end up with one way of getting to a point or a different way of getting to the same point. Right? So if we just rolled all the way under like this, what would that be? That would be pitch of negative 135 degrees. Our plane's flying along upside down now. But what's another way to get there? Another way to get there might be a rotation and then some pitch and then a roll. Right? So it's not a single way to describe how you end up at that place. Well, as far as displacement is concerned, it does matter the steps you took to get there. But the end result is they look the same. And so sometimes that's an issue. There's some other issues that happen with Euler angles that we'll talk about a little bit later. But let's just write down a matrix for each of these kind of transformations. So if we have something in object space, and we want to put that back in upright space. Right? Upright space corresponds to the whatever our standard is for the direction of the original coordinates. We have our plane, or the object that has changed. To do this, we need a matrix for each of the pieces. So roll is also called bank. These also have some other names. There's some other things that you'll see sometimes. You'll see yaw, pitch, and roll. You may have heard that term before. Sometimes there's and these are slightly different, but they're all similar. Sometimes you see it like this. Sometimes you see it in there's different ways. Sometimes you see it from like mathematicians where they use Greek letters to describe the different angles. There's a lot of different approaches, and they're similar, but some of them are different. Pretty close. Different approaches for these different situations. These depend on the industry that needed it and created it, and so there's some differences. All right, but what happens if we want to go we want to describe a matrix that describes these different positions or different aspects? What did we say that bank corresponds to? Bank corresponds to a rotation about the z-axis, right? So this is what we have created before when we were rotating things using 2 dimensions, but we say what happens in 3 dimensions. If the angle that we want is B, our rotation for bank, this is coming back from the object, trying to put it back into upright space, right? So here's our matrix in that scenario. The matrix for pitch, we're revolving about which axis? Pitch is this way. So that's the x-axis is where the revolution, the revolution is happening in that direction. So what do we have? This means that these pieces, right, the x part is left alone, and it's just going to change the other values. And what happens? We again, let's just do 0. Cosine p, sine p, negative sine p, and cosine p there as well. And then the heading is our revolution about the y. So those parts stay the same. And it turns out that the y, because it seems different when you look at the clockwise, anti-clockwise aspect, that this is almost the same, except the negative sign trades places. Now, this is probably a bad choice. I'd used what the authors used. There is a trigonometric function called that, which is the hyperbolic cosine and then the hyperbolic sine. That's not what I mean here. I just mean the cosine of something.
What is hyperbolic?
Don't worry about that right now. We can talk about that at a different time. So these are really, again, cosine of h, cosine of p, and so on. All right, same thing up there with b. And so to rotate from object space to upright space, we would create a matrix, and we have to do this rotation in kind of the opposite order. Typically, we're going heading, pitch, bank, but we're going from object space to upright space, so we go bank, pitch, heading. And we just multiply those matrices together. All right, and that takes us from the object, wherever the plane happens to be, to get back to the original, whatever the original orientation is, to figure out what's happening there. If we wanted to do that in the opposite order, we need to use M inverse. But what's the nice thing about these matrices? These matrices are rotation matrices. And if you remember, we said, well, we showed that it works for 2-dimensional before, but it works in any rotation matrix. A rotation matrix, the inverse, is the transpose of the matrix. What does that mean? You swap the rows and the columns, right? So the first row becomes the first column, second row becomes the second column, third row becomes the third column, and we have the inverse right away. So what do? We would calculate this. This would tell us how to go from object space to upright space. The transpose would tell us how to go from upright space to object space. And that's with rotations involved. Now, there are lots of issues that come up, some other things. Something that we'll talk about later called gimbal lock, which is a problem that happens with Euler angles. Some other concerns and some things that happen. But if we're thinking about matrices for doing these calculations or doing these operations, there can be a lot of calculations that take place. But in most systems, ultimately underneath, we end up doing that. There are other techniques. Quaternions we've mentioned briefly. Quaternions are another way to deal with this, but eventually at some point there's some matrix calculations involved. But in some cases you can save on certain other calculations. We'll come back to that just very briefly. But the idea here is that all of this is involved with being able to translate or transition from one coordinate system to a different coordinate system and still be able to talk about things. Still be able to say, hey, object, go to your left, and its left be clear what its left is. Or, hey, object, go to my left, which is no longer the object's left, but is some direction that we can specify of how far to go, which direction do I travel. So we'll come back to all of this and do a couple of things with labs that involve not so much the three-dimensional version, because we're still going to focus pretty much on using Pygame, but having these ideas out here of how to do these things, so that in three-dimensional graphics and things that you're doing in later courses, you'll still be able to you'll have at least an idea of what's happening, so that when you see it again, you can build on that. All right, so again, as usual, any questions, let me know. Email, Discord, whatever. Just make sure that if you have any questions, that we get those resolved.